Let's do chapter 14, problem 1. So a reading of the problem: sketch on an HR diagram of what you expect the evolutionary paths of a 2 solar mass and a 15 solar mass star to look like. If we answer this question, we're basically going to reveal all of the content in chapter 14, stellar evolution. So let's proceed first with the 2 solar mass star. Now the approach that we're going to take in our answer is to make full reference to the very good diagrams and pictures that are in our chapter. So the first thing that we're going to do is to go to page 379. And on 379, we see that for a 2 solar mass star, then this is the main sequence, then it comes in as a protostar along this path right there and finds its home as a 2 solar mass star on the main sequence. So as it comes in from a collapsing interstellar dust cloud, it goes through this more luminous than the final destination phase, so it goes through a red giant phase as it's collapsing. It's not a red giant phase because it's expanding. That comes after it leaves the main sequence. It's now a red giant phase because it's still contracting. It hasn't reached its final size yet. So then it arrives on the main sequence where it will stay for a certain amount of time. So the next question that we want to say is, what is its luminosity there on the main sequence? And in order to find that in our text, we go to page 352, where we have a very good HR diagram showing you the various luminosities for the various masses. And we see that for a mass 2 star, it has a luminosity of 10 solar masses. 10 solar luminosities. The next question we want to ask is, how long does it stay on the main sequence? Well, we know from the equation on page 371, so now this is page 371. The first one is page 379, where you want to reference that, and this luminosity we found on page 352. So on page 371, we find the equation for the lifetime on a main sequence star, and that's given to us as t equals t to the 10 to the 10th times the luminosity divided by the mass, or upside down, the mass divided by the luminosity. Now in this case it's 10 to the 10th, and the mass is given as 2, and the luminosity we have already found as 10, so it is equal to 2 times 10 to the 9th, or 2 billion years is the amount of time that it will spend on the main sequence. Let's compare this to our sun, which will spend 10 billion years. So it will spend significantly less time on the main sequence than our sun because it is larger. It is 2 solar masses, not 1. And as you go up in increasing masses on the main sequence, the core temperatures become higher and higher. Sure, the mass gets larger, but the core temperatures get so much hotter that even though the star has more fuel to burn, it's burning it at a much faster rate. So as you go up the main sequence, the lifetimes get shorter and shorter and shorter, until when you reach up around a 25 solar mass star, then the lifetime is measured in millions of years, no longer in billions of years at all. So the next question that we want to address is when this does start to leave the main sequence, because what is happening is that its core fuel of hydrogen has been burnt out. It turned completely into helium. So it now has a pure helium core, but the temperature in the center is not high enough for helium to burn and turn into carbon. So it just sits there inert, and therefore the core collapses. And as the core collapses, because it's not generating enough heat anymore to retain its initial expansion, then it draws in fresh supplies of hydrogen that have just been sitting up in the upper layers of the star where it wasn't hot enough for them to turn into helium. It draws new hydrogen into the high temperature region, and then that starts to burn in a shell around the previous core. And since that shell is near the surface of the star, then it gives it increased luminosity. It shines through less layers than it did when it was in the core, and it also drives those layers up and out, so the star becomes larger, and with a larger surface area, it's generating more luminosity. So all of that means that the star is going to start moving into a region of higher luminosity. We say it leaves the main sequence. Now, the first thing that it encounters as a 2 solar mass star when it leaves the main sequence is indicated on page 375. On page 375, you see what you have is the instability strip. This strip is such that has a combination of density, luminosity, and temperature, such that if any star happens to have that combination of density, luminosity, and temperature that puts it in that region, then it is going to pulsate like a tea kettle. First, it's not going to be able to release all of its radiation because the surface is a bit too dense. So the radiation piles up under the surface until the surface can't contain it anymore. Then it bursts through the surface, and then it's gone. So it's not pushing pressure against the surface anymore, so the surface falls back down by gravity, and it seals off the escaping gas or radiation, and then it builds up again, pushes through, and then seals off again, and builds up again, and pushes through. So the instability strip has 2 regions. First, the lower region, the pulsations are in the order of 1/2 a day. And these type of stars are called RR Lyrae stars, after the prototype of them. But in the higher regions, for higher luminosity, where larger stars will cross the instability strip, then the pulsations are on the order of 1 to 100 days. And this works exactly like the lid on a tea kettle, which will sit there fine while the water is boiling until the steam builds up to too much. Then the lid will pop open, the steam will escape, and there's no more pressure pushing the lid up, so the lid falls back down. And a little while later, it pops up again and pops down. So this is known as the instability strip. Now, it falls into the main sequence right at the 2 solar mass mark. So the first thing our 2 solar mass star does is it enters the instability strip and spends amount of time as a pulsating yellow giant, and it is in the RR Lyrae region. After it finishes doing that, then we can trace its sequence around on page 379 all the way through. On page 379, we have a very good chart, and let's go to a fresh diagram right now. We leave the main sequence right at that point, and we become an RR Lyrae star for some time, a yellow giant region, and then the same sequence continues to happen, and that is that there is more and more luminosity generated due to these shell burnings, and so the star continues to get larger and larger in its luminosity, not because its temperature is getting greater. Actually, the surface temperature is dropping. It's cooler because the surface is so much further from the core now, where the heat's coming from, but because it's expanding, the surface area is so large. And remember, the luminosity is a product of 2 factors, the surface temperature and the surface area. So even though the surface temperature is dropping, which means it's moving to lower temperatures, the surface area is growing so much that it goes into a giant star. And then it goes back and forth across the instability strip to a yellow giant again, then back into a red giant again. And after it goes back and forth several times, then it goes into the high red giant regions, and then it starts to pulsate again by a different mechanism that we said before. Actually, what it's doing in this region is it's finally enabled itself to burn helium. The core temperature has become so hot due to contraction that the helium is now actually able to turn into carbon and a little bit into oxygen. So this is as luminous as it gets. This is the peak right here, and it also starts to pulsate in a different mechanism, and this is called a Mira type pulsation. Now, the death of the star starts to appear because it is now so intense in its heat generation that it's blowing its surface areas, its surface layers off of the star itself. And as the surface layers blow off of the star, then its area becomes smaller because the surface is gone, the area under the surface has a smaller radius than the surface, and then that area gets blown away again. So the star continues to have a smaller and smaller size. But as these layers are blown away, then what becomes visible is the core itself, which is at a very high temperature. So two things happen. The core comes nearer the surface, which means the temperature you're seeing on the surface goes up, but the surface area goes down because it's blowing away all of its layers. So the luminosity stays about the same as it goes off in this direction. But you see the temperature is going up because the core is becoming visible, and the area is therefore going down in order to keep the luminosity the same. But finally there is only the core that is left, and when only the core is left, it's very, very tiny. It's about the size of the Earth itself. So even though it's very, very hot and the temperatures stay very, very high, the overall luminosity goes down and down and down because the outer layers have continued to be shred, and what you have left is a very tiny core with a very tiny surface area, so it now enters the areas that we call the white dwarfs. So these steps are spelled out very, very well for you in the chart and in the diagram on page 379, where you should study them quite a bit. Now, let's proceed to question B, which is a 15 solar mass star. And we'll go through a similar sequence of steps. The first thing that we want to do is understand that it is also a protostar. So it will come in from an interstellar cloud at a very high luminosity because it has a very large surface area, and it will come in much quicker than the star that we looked at before because it is larger, it has higher core temperatures, and everything happens faster, and it finds its home at the 20 solar mass point up on the main sequence itself. The next question is we ask, what is its luminosity? And again, we go to page 352 and look at an ordinary HR diagram, and we see that for a 20 solar mass star, we are looking at a luminosity of about 10 to the fourth. So we now ask the question, what is its lifetime on the main sequence? That comes from page 371. This came from page 352. And its lifetime is given as we used a moment ago for the 2 solar mass star as 10 to the 10th times the mass over the luminosity. So this is 10 to the 10th, and the mass is 20, and the luminosity is 10 to the 4th. So what we're going to get is 20 times 10 to the 6th. In other words, it lives for 20 million years, which is nowhere near, well, let's check that luminosity. Well, the problem is that we're investigating a 15 solar mass star, not a 20. So I switched to a 20 for some reason, but the mass is 15 solar masses. So we'll put in the 15 so we get the numbers correctly, 15 solar masses. So when we put the 15 instead of the 20, then what we get is 15 million years. 15 times 10 to the 6 years. So it lives 15 million years, whereas our own sun lives 10 billion years, and a 2 solar mass star lived for fewer billion years. It lived for 2 billion years, or 2 billion years, our sun lives for 10. So this only lives for 15 million years, and then it starts to leave the main sequence. Now, when it leaves the main sequence, then it also goes across the HR diagram at the top, and this very good picture of how it travels is given on page 382. The first thing it does again is that it is burning hydrogen in its core, and then it starts to have no more hydrogen to burn. It's all helium in its core, so it starts to burn hydrogen in a shell around the core. But something is very different about this star than was about the smaller star, and that is that its core is hot enough to also burn helium. So it's burning helium and hydrogen at the same time. So it is a very, very strong heat source at that point, and it is expanding and driving out to larger and larger radius. So therefore, as it goes to larger radius, it starts to cool. Now it also crosses the instability strip, but it crosses the instability strip at a higher luminosity than did our 2 solar mass star, and in this higher luminosity, then it is pulsating with periods between 1 and 100 days, whereas our smaller star only pulsated with a period of a half day, and this upper region of the instability strip is known as Cepheid variables. So it becomes a Cepheid variable for a while. So what we're illustrating is that all of these stars on the HR diagram are Lyra stars, Cepheid variables, red giants, yellow giants, are not different types of stars. They're all just one type of star, that is a main sequence star at different stages in its age or evolution. So as we walk across the 382 diagram, we see that we do go into the instability strip, and then we finally cross over it to the other side, and it is now a red giant, and is now doing so much burning in its shells. As each shell finishes burning, it contracts a little bit more, and it brings more fuel into the high temperature region, and everything is hot enough so that it can burn all of its hydrogen into helium. It can burn all of its helium into carbon. It can burn all of its carbon into oxygen, all of its oxygen into silicon, and all of its silicon into iron. But once it reaches an iron core, iron refuses to burn. Iron will not burn, so it cannot go any higher in the element sort than iron. So what happens is there's no more burning in the core because now iron is there and now iron doesn't burn. Without the heat, the core collapses. And as the core collapses, all the other parts of the star rush inwards. And when they hit the iron core, they bounce off and the star explodes into a supernova.